Okay.
Okay. Hi everyone, and today we're hosting Weihao Sheng. Should I say Sean or Shen?
Sean. Yeah.
Sean, yeah. So Weihao Sheng investigates the neural mechanisms underlying cognition. Specifically, he focuses on reasoning, decision making, and learning by using complementary techniques, including optical imaging, viral genetic tools, in vivo electrophysiology, and behavioral assays in rodents. He is now a research assistant in Yang's lab at Shanghai Tech University. He did his PhD and finished his PhD last June in the same lab at Shanghai Tech University. And before that, he did his bachelor's in microbiology at Shandong University. Thanks a lot, Weiho, for accepting our invitation. Go ahead.
Okay. Yeah. Thank you, Dr. Najafi, for inviting me to this journal club. And hello, everyone. I am Wei Hao from Yang's lab at Shanghai Tech University, and we are a small-scale research university located in Shanghai. And before I start, I need to say that there are some updates in this manuscript that we have not yet uploaded to the bioarchive. So if anyone see anything that you did not see on the bioarchive and you don't understand, you can feel free to ask me. Yeah, so let me begin my story. The world is noisy and uncertain, and you can think about a very ordinary decision. You're about to leave home on a summer afternoon. The sky looks fine, but you know storms can appear quickly. So the question is, do you bring an umbrella with you? You don't have the perfect information, and the outcome is probabilistic. So similar structures show up everywhere in our lives. A stockbroker must decide to invest or withdraw based on the limited knowledge of the market, and a clinician has to decide on a treatment based on the incomplete symptoms and a few tests. In all the three cases, we make choices under uncertainty, often based on limited knowledge. And we all want to make good decisions in these situations. And what is a good decision? So there are many answers to it depending on the field of research. So in economics, there is a classic idea called expected utility theory. The intuition is very simple. You have many options and you combine how valuable you think it is. It's called utility, with how likely they are. And you derive an expected utility. And you simply choose the option with the highest expected utility. And also in statistics and computational neuroscience, there's a closely related ideal called Bayesian inference. You start with prior beliefs, update them with new evidence, and you end up with a posterior belief. The good decision is the one that best matches the information available to you. I'm sure that many of you are familiar with the Bayesian frameworks. And these two theories are are just two good examples to tell you how to make a good decision, or we usually say how to make an optimal decision. However, when we look at real human behavior, we repeatedly see systematic deviations from these ideal choices in economics and psychology. So, 50 years ago, two brilliant psychologists, Tversky and Kahneman, discovered one of the most influential phenomena in modern economics and psychology. They showed that people routinely overestimate rare events. In their own words, and I quote, people act as if rare events are more likely to happen than they actually are. This phenomenon is usually described as the overestimation or overweighting of rare events. And this idea becomes a cornerstone of behavior economics, and Kahneman later received a Nobel Prize in part for this work. This behavior pattern is widely present in many real-life scenarios. For example, many people are obsessed to win a big prize, and some of them even evolve into gambling addiction. And there's also a phenomenon called overinsurance, which means people are willing to pay extra money for those rare exceptional events. And also, many people are feared of traveling by planes, overestimating the probability of a plane crash. However, among these examples, there's a shared property of rare events. So think about it. What defines a rare event? It is simply the probability, the fact that rare events occur less frequently than common events, and we call this property the statistical rarity. But in most classical conditions, rarity almost never comes alone. It is typically tangled up with other powerful factors. For example, in gambling, rarity comes with high value, and in insurance, rarity is combined with loss aversion, and it's another psychological phenomenon. And in the last case, rarity is entangled with emotion. So when we see the term overweighting of rare events, what exactly is driving it? Is it the brain responding to the statistical rarity itself just because something is occurring less frequently, or is it the brain responding to the rare events because it is either big, salient, or emotionally charged? This brings me to the central questions of this talk. Does statistical rarity have an independent impact on behavior? And does the brain process infrequently encountered events in a fundamentally different manner from frequent events? So let me give you a quick view of the following slides. I will first present the behavior tasks in both human and mice, and then show you the roles of the posterior parietal cortex using optogenetics. And after that, I will use the in vivo recording results to show what PBC neurons are doing. And finally, we proposed a model to explain the dynamics in the behavior. So let's start with the behavior. We first designed a human task based on the two alternative forced choice task, a 2AFC structure so that the human subject must choose one option from the two alternatives. We instructed the subjects to make decisions based on the sound cues to collect maximal rewards. In each trial, a subject needs to press an start button, then hear a sound, and then press the left or the right button to receive the outcome. And the outcomes are just animations on the screen that shows money or no money. To isolate statistical rarity from other confounding factors, we used probabilistic rewards. So, for example, when the subject hears a duck sound and chose left, there's an 80% probability of getting the reward and 20% of not getting it. And if the subject chose right, there's still a 20% probability of getting the reward and 80% not getting it. And we call these trials with higher probability as common and trials with lower probability as rare. And I need to emphasize here, and very importantly, that we use the same outcomes for both common and rare trials. This means that for example, for a duck left reward, the subject saw an outcome of 3 coins on the screen, and then if the subject experienced a duck right reward, the subject saw exactly the same animation that showed 3 coins. So no matter it is a common reward or a rare reward, the magnitude is the same, and the subjects could not tell whether a trial is common or rare simply based on the outcome received. They must combine the stimulus, the choice, and the outcome to know if it's a rare trial or a common trial. And we altogether use 4 different sounds for the human task, and they are pseudo-randomly interleaved in the sequence. And 2 of them had a higher reward probability on the left, and 2 of them had a higher probability on the right. So these contingencies were not informed to the subjects, so all the subjects must learn them through trial and error. And again, I need to emphasize that in this task, the statistical rarity is not tied to any of the stimulus, choice, or the outcome. It is the infrequent combination of the stimulus, choice, and outcome that defines statistical rarity.
Question. question, just making sure because it's crucial to understand the behavior. So if I understood this correctly, so they start the trial by pressing that button, that S button. Then a sound is played. It's either, let's say, a duck sound or a cat.
Yeah, it's one of the 4 sounds.
Okay, it's one of the 4. So there are 4 types of animal sounds played.
Yeah.
For, let's say, the duck, 80% there is chance of reward if they click the left button.
Yes.
Right? For
and
the
20%
cat sound,
for right.
Right, and 20% for right.
Yeah.
What is it for the cat?
It's the same. So these are just 2 different sounds, but they share the same rule.
Okay. So 2 of the animal sounds give 80% reward on the left and 20% on the right. And 2 of the other animal sounds are associated with the opposite, 80%.
Yes.
80%
right.
But that is 80% right
left.
and 20% left. Okay.
Yes.
And then the rarity is, so the rares are right for cat and duck. It counts as rare because that's less likely to give them reward. Is that the rare trial?
No, actually the rare trials are predetermined in the sequence. So so we how to say it? So it's like when the subject presses, and for example he heard a duck sound, pressed a left button, and when he or she received the no reward with 20% probability, it is also a rare trial.
Correct. Yeah. Correct. So the less frequent, the less likely outcome will define whether that trial was rare or not. So if they press left for the top 2 sounds, they press left and didn't receive reward, that's rare. Or if they press right and received reward, that's rare. The opposite is true for the bottom. Okay, sounds good. All right, thanks.
Yeah, so common and rare trials are not just associated with rewarded or not. Yeah.
Yeah.
And so what's the optimal choices for this task? So once you figure out these contingencies, of course you will know that if I hear a duck sound, and I should always press left, right? Because it gives you it is more likely to get the reward. So we also used a simple stimulus-based Bayesian model, and it also tells you the same, that after maybe 100 trials, you should always choose the side with the common reward, and the common reward is the side with the higher probability. And we defined these choices as the correct choices to assess the performance. So for duck and cat sounds, you should always choose left, and for the frog and the bird sound, you should always choose right. And of course, most subjects learn the task and eventually reach the expert level performance after 100 of trials. So what's happening before the subjects learn the task when their performance was still lower? We defined a naive stage as performance below 65% accuracy. And we calculated the probability of repeating a previous choice based on whether the choice was rewarded or not. So the conclusion is we found that subjects followed a stimulus-based win-stay-lose switch strategy. So specifically, the subjects were more likely to repeat a rewarded choice and to switch from an unrewarded choice when they heard the same sound in the immediate next trial, but not when they heard a different sound. So you can see that for both duck sounds, they would have this win-stay-lose switch behavior, and not if the next sound is another sound. So this shows that humans followed a stimulus-based win-stay-lose switch strategy in the naive stage. And this stimulus-based strategy not only applied to the immediate next trial, but also extended to a few trials later. So when 2 same stimulus trials were spaced by other intervening trials, So for example, because our trial sequence are randomly interleaved, there could be two duck sound spaced by k other trials of different stimuli. And we call this we call this trial the same stimulus trial. We call it as the next same stimulus trial. And the number of intervening trials between these two duck sounds was defined as k. So we checked whether rarity had any effect on these choices. We found that
is
reward.
this still a naive about naive animals or experience?
Yeah, it's all in the naive stage.
Okay.
Yeah, so from now on, almost everything I'm talking is about the naive stage unless I stated otherwise. So we checked whether rarity had any effect on the choices. We found that a rare trial produced a significantly stronger stimulus-based wastage tendency than reward in a common trial. So as you can see here, when the same sound reappeared later, there was an even higher probability of repeating a rare rewarded choice than repeating a common rewarded choice, despite the fact that I used the same outcome magnitude for both common reward and rare reward. So this is astonishing because on the trial level, the outcome magnitudes were the same. And also, if on a session level, if you repeat a rare rewarded choice, you would have less probability of getting the reward. So this behavior is definitely counterproductive. And of course, this rarity-induced choice preference, and which we call the rarity-induced bias, also deviated from the optimal strategy as predicted by the Bayesian models. And this is also Bayesian models running in the naive stage. So what's more, we found that this bias was most pronounced during the early phase and diminished as subjects achieved an expert level of performance. So
could you give a pause, Weihao? Did I understand this correctly? That when they make a choice and they get rewarded, on the next trial, they will repeat, they're more likely to repeat that same choice. And this is similar for both rare and common.
Yes,
or you said that it's more likely to happen.
Yeah. For example, you can see here, for both common rewarded and rare rewarded trials, they are both more likely to repeat that because the repeat probability was like over 80%. But the point is here, following a rare rewarded trial, they had higher probability to repeat that compared to a common reward trial.
What is that K intervening trials? How is that?
Here
you mean
we
that it
put all
lasts
K
longer?
We will talk about the repeat probability versus K later. But here it is K equal to 0, 1, 2, 3 all pulled together.
Okay. And then so anyway, they're more likely to repeat it if it was a rare trial that got rewarded. So it's like a very salient stimulus that makes them just repeat that. And then what is the thing? What are the two bars on the right side that's if it doesn't get rewarded? The orange and the brown bars, what are those?
Yeah, if they did not get the reward, they see the no coin, and it's not significant different. There is a slight trend, but I mean it's not significant. Yeah.
Okay.
Yeah. So as I just said, that this bias would gradually diminish as the performance goes up. So when you subtract the rare reward repeat probability with the common reward repeat probability, and you have this delta. So when it goes down, you will see that when the performance rise to like 80% or 90%, these two bars are reversed. It is the repeat probability following a rare reward is lower than a common reward when the performance are higher. So based on this result, we would say that statistical rarity alone is sufficient to drive a robust bias in human decisions in the naive stage. And so when we discovered that, what about animals? So we developed a parallel 2AFC task for mice with two distinct sounds. So these are water-restricted mice poked into the center port, then they heard a sound and then they choose left or right to get the reward. So similar to the human task, for stimulus A is a pure tone 5K hertz, and left is the frequently rewarded side, and for stimulus B, right is the frequently rewarded side. Again, we focused on the naive stage of mice when their performance was below 65% and found that mice behavior mirrored human behavior, also showing higher repeat probability following a rare rewarded trial. This bias also diminished progressively as mice learned the optimal strategy, and they have the higher performance later. So we want to know if the strength of the bias depended on the level of rarity, and we varied the probability of common and rare trials in separate groups of mice. So we trained other mice with higher rarity level, which means that the rare trials are much rarer, and we found that the bias was even stronger when the rare events became rarer. This shows a graded effect sensitive to the rarity level. And when this, you can see here that for the rewarded trials, after a reward, when the rare events were much rarer, you can see higher delta repeat probability, which is the repeat probability between the difference between the rare trials and common trials. And as you can see here, so when the probabilities were 80 versus 20, there was not a significant trend for the unrewarded trials. But when the rare events were rarer, you start to see a more significant trend for 10% and 5% right here. So mice were more likely to switch from rare punishment trials than these common punishment trials in these rarer conditions, which means that the rarity-induced bias was not only limited to these positive outcomes, but it also applies to negative outcomes. And these results show that the rarity-induced bias is quite conserved across humans and mice, and it scales with rarity level, and it applies to both positive and negative outcomes.
Question.
And
okay. Could you? So first of all, very interesting, and like I'm loving the way you're describing this. So the blue and green curves make sense to me. The brown and the orange. Let's look at this one that shows a clear effect. So let's focus on the brown one. You're saying that if it was a common trial and they did not get rewarded, not get rewarded, on the next trial, they're still more likely to repeat the choice?
That's because these mice, we were measuring the behavior of these mice in the naive stage, and I mean all mice have a strong tendency to just stay with the same choice. It's called perseverance. So as you can see here, that all three groups of mice had this kind of perseverance behavior, and they all had an overall repeat probability above 50%. That's why all the bars are above. So
it's basically win, stay, lose, stay. So it's a stay whether win or lose, but stay more if it is win. So that's what I see from the comment.
Yeah, but if you can hypothetically subtract all these four bars with an average, for example, subtract all these bars with a 70%, you can see the classical win, stay, lose, switch behavior. But yes, I mean the behavior is like complicated here.
Right, and this is all again naive. So when they don't know the task structure, they're just more likely to repeat. the rare events specifically. Repeat everything, particularly the rare rewarded events.
Yeah, yeah, it's actually they were more likely to repeat a rare rewarded choice and switch away from a rare punishment choice. So it's like
Right.
amplifying the Wednesday lose switch effect.
Yeah, I mean, the switch, it's near 50%, so I wouldn't,
Yeah, yeah,
it's,
yeah, I see what you mean. Yeah.
so you're talking about the relative thing, but compared to a common, they're more likely not to repeat. That's how I would say it, not to switch. They're
Yeah,
less
yeah,
likely to
yeah. Right,
repeat,
right.
to be more accurate.
Yeah,
Okay.
right.
Yeah.
Um, yeah. So back to the key question that we talked earlier. The repeat probabilities were computed between these two same stimulus trials, and previously we showed that between the two trials there are other intervening trials, and so we wondered how would the number of k, how the number of intervening trials affect the repeat probabilities. So we found that the influence of common rewards decayed rapidly as k increases, which means that for between the two A trials, when you have more B trials in between, the the repeat probability following a common reward will rapidly decay, and the the higher the probability is, the more it decayed, the faster it decayed. However, for a rare rewarded trials, this is not the case. Instead, you can see that repeat probabilities not only not, not only did not decay, but also raised to a saturating 100%, which means that if you have more B trials between two A trials, they would almost 100% repeat the rare rewarded choice in this A trial. And this is quite astonishing because it means that rare rewarded trials and common reward trials may have different processing mechanisms in the brain, but like it's like separately processed. Yeah, and additionally, we can see here when k equals to 0, when the next trial is the same stimulus trial, you can see that rare rewards could immediately trigger a strong win state behavior than common rewards, even when k is 0, if the rare events are rare enough, but not here. So
Question,
similarly, the influence.
question,
Uh-huh.
if you could go back. Actually, one important question, because all of this is about naive. How do you decide which mice are considered naive, or do you have some metric to call a mouse naive? Is it like
Yeah, it's the average
reward?
performance below 65.
Okay, you did mention that. Sorry, I forgot. Okay, then the other question here. So the bees in between, are they common or rare?
The blue ones are
B, no,
common
the B,
rewarded.
the B. No, I'm looking at your schematic where you have A, B, like up
Ah,
there. Yeah, yeah, yeah. So the
this is just
ones
a
in between,
schematic.
are
So
they?
yeah, so so this diagram show both the same stimulus for A and for B. So for example, you would have, yeah, here. So for example, you would have A trials for, this is k equals 2, and for here this is like when we were computing the repeat probability for k equals to 0, we used all the possible case. So we used this pair, this pair, this pair, this pair.
I'm asking something else. Can I ask my question again? So let's say K
Uh-huh.
of 2. Actually, the previous one was a good one. If you could go to that one, the previous slide.
Mm-hmm.
Okay, let's say K of 2, A, B, B, A. A
Mm-hmm.
was a
Yeah, here.
rare rewarded. Let's say A was a rare rewarded trial, because you told us if A was a rare rewarded trial on that second A that comes after two B's in between, they tend to repeat the choice of A now. What I'm asking is that does that depend on whether those two B's in between were rare or common?
I see what you mean. We did not separate that in our calculation, so it's kind of like mixed in the calculation. And yeah, that's a good point. But currently it's like all mixed, and these two bees would have a 20% probability to be a rare trial.
Right. So the point is
Yeah.
that it has a long-lasting effect. A rare rewarded
Yes.
trial has a long-lasting effect, but a common rewarded trial does not. It washes away after 2 trials.
Yes.
Right.
So I go on.
Yeah, thanks.
Okay. So similarly, we found that the influence of common punishments also decayed over time, and the axis here is the repeat probability, and you can see that the common punishment trials showed increased repetition, which means reduced. They are less likely to switch away from that side, while the influence of rare punishments also strengthened with increasing intervening trials. So this result suggests a kind of asymmetric separate neural pathway for processing these common events and rare events.
I think I really have a little bit of difficulty with how. So what I'm seeing the common punishment is that after common punishment at K0, they're already more, they're at about chance in terms of repeating or not. But then they become more likely to repeat the same choice as the common punishment. But for the rare punishment, they're more likely to switch. Right. So the common punishment, they repeat it more, but for rare punishment, they're more likely to switch.
More. Yes.
Right. But is that not surprising that they repeat after common punishment, and even more if there are more intervening trials? The rare punishment makes sense and is aligned with the rare reward, that in general, rare outcome has an impact. If it was reinforcement, they repeat it more. If it was aversive, they switch. But the common reward, okay, the fact that the repeat went away in the previous plot, which I guess it went to about 50%. Can we double check yeah, that one kind of makes sense. No, not quite, because for the 0.95, it actually switches. It's a bit complicated. I don't quite get the common trials outcome, the effect. We can keep going, but it's pretty hard. I cannot put it together. That why they would repeat it. Maybe you have a way to explain it, but I don't understand why, in an intuitive way, why they would repeat a common punishment even more with intervening trials.
Yeah, that is indeed puzzling, but I don't have an explanation here. Yeah.
Yeah. Also, you have a lot of conditions here, like in the previous slide for the 0.955 case. They're switching after a common reward, which is very.
Yes.
What does that? So why would I wonder if it would give more clarity if you were going to separate these conditions based on what the outcome of those intervening trials were. So whether they were common reward, I think that is perhaps making a big difference here. And if you
So well, here I think I have an explanation for the point here. So for example, when the k equals to 3 and you have 3 b's between these two a's, right? And the 3 b's are more likely to be rewarded on the opposite side, right? So it's kind of like following a common reward here, and you get if you stayed with the same side here, and you are less likely to get the reward in these 3 b's, right? So the more b's occurred, the more likely that the switching to the other side makes it more likely to have the reward.
Right. So then the switch that we're seeing. Exactly. So then the switch that we're seeing is a secondary effect. It's as a result of those intervening b's that more likely happen to be incorrect. And so that appears as a switch that you're trying to link to the common reward, But it's not really about that. It's about the intervening incorrect trials. And that's what I'm saying, that I really think these plots will get cleaned up if you take into account what happened during those intervening trials. Because right now it seems like you want to say everything is the result of that common reward, but that's not the case. Across these
I see
plots,
what you mean.
the outcome of the intervening trials is different across these three plots. So that's why we cannot really compare the blue curves with each other.
Yeah. I see what you mean. We actually did try to use a simulation that we that so the point here is we hypothesize that if the rare reward effect could be explained by the intervening trials between them. So we would hypothesize that if the B trials had a similar effect on both common reward and rare reward trials, then it should decay. I mean, it could decay slower, but it should also decay. I don't know if you understand my point here, but the data shows that it does not.
Right. Right. Okay.
Yeah, we do have a mini model here, but we did not show it here. Yeah.
Sounds good. I guess we can continue.
Okay. So, yeah, for the first behavior part, we found that statistical rarity alone is sufficient to drive such a robust heuristic bias in both humans and mice, and the rare events can cause a graded and persisting influence on choices, and which can apply to both positive and negative outcomes in mice. And so now that we have found the bias, we need to know its neural mechanisms. So what brain areas could possibly be involved in this bias? And decision making is a complex process that requires involvement of many brain regions. And for our discovered the rarity-induced bias, there are at least two requirements: that this brain region should be involved in trial history, and it should guide decisions. So the posterior parietal cortex happens to be a good candidate for mediating the bias. There are many previous literatures that show PBC encodes many kinds of trial history, including the stimulus history, the choice and outcome history. And also, PBC is heavily involved in encoding and guiding decisions. So we first targeted PBC to see whether it is causally involved in mediating the bias. And we used AAV-based optogenetic opsin, the EMPHR3, with the promoter CAMK2 to target mostly excitatory neurons in the PBC. And 4 weeks after virus injection, we trained animals to learn the task, with the PBC being inhibited in one of the two epochs of rare trials. So we inhibited some mice with the outcome epoch of rare trials inhibited. And this is the time when the animals received the rare reward or punishment. And we also trained other mice with the stimulus choice epoch being inhibited. And this is the time when the stimulus was presented and their choices were made. So, although we know that the outcome epoch is when the animals can tell if an event is common or rare, we found that inhibiting PBC during this epoch had no detectable effect on this rarity-induced bias. You can see the repeat probabilities after a rare reward trial is still higher after a common reward trial. The conditions are similar to in the control mice. So PBC activity during this period was not necessary for the bias. However, inhibiting PBC during the stimulus choice epoch of rare trials completely abolished the bias. Yes?
Could you go back to the previous one? So I'm focused on the plot, right? This one, the bar plot. So the one without up to looking at common, and then the one with up to common comes all the way. So what is common? Which two conditions should we compare?
you can just compare this two because we inhibited all rare trials in this design. So it's like all rare rewarded trials and all rare punishment trials are being inhibited using
But
optogenetics.
can we compare control common rewarded with up to common rewarded? Is that not what we want to compare?
Uh, no, because these are another group of mice. These are not the same group. We actually had a comparison for the same for the stimulus choice epoch inhibition within the same mice, but we do not have it here. Yeah.
Okay, but it would make sense to see in the same mouse how control common rare compare with control with up to common rare, no?
Um, I
Because
would
maybe
say
this mouse didn't have the effect of increase repeat after a rare. I understand you're showing increase repeat after an up to rare relative to common control, but I would like to compare that with the, yeah. So I would like to
okay.
see common control, common rare
We do have
compared to
comparison here.
common
Yeah,
control.
yeah, here. We do have comparison here, but I showed it here. Yeah. So it's
Okay,
like
but
we used a delta repeat probability, which is the rare reward minus the common reward. And you can see these two here. For control group, it's the blue one, and the outcome opto group is the yellow one. There's not really a difference between the delta repeat probability here.
okay,
Yeah.
sounds good.
So what we found is that inhibiting the PPC in the stimulus choice epoch, when they heard the stimulus and made decisions, completely abolished this bias. And you can see that the the repeat probability after a rare rewarded trial is no longer higher than the repeat probability after a common reward trial here. And when we compute the delta repeat probability here, you also see a significant difference for the stimulus choice opto group compared to the control group and the outcome group. And to control for the inter-animal variability, we also perform comparisons within the same animal for the stimulus choice epoch inhibition. We use the alternating control and optogenetic sessions in another group of mice, and we observe the same reduction in the bias. So each line here represents one single animal. So you can see that the phenomena is also present within the same animals. And since that the PPC has been widely reported to encode choice and reward history, it is possible that inhibiting PPC during the stimulus and choice epoch also affected the choice and reward history in general, and further produced the reduced bias that we saw earlier. So to rule out this possibility, we also inhibited the same epoch in a subset of common trials in another group of mice, and what we observed no effect on the choice repetition for these common opto trials. So this rules out the possibility that we are inhibiting the reward history or choice history in general. And therefore, the optogenetic effect was specific to the impact of rare rewards rather than the rewards or of choices in general. And this result shows that PPC activity during the stimulus presentation and choice formation epoch of rare trials, but not during the outcome epoch, was required for generating this rarity-induced bias. And because the rarity-induced bias led to suboptimal decisions, and abolishing this bias should improve performance. And indeed, we observed higher performance in the next same stimulus trials, also in the stimulus choice opto group. And in addition to these expected effects, we found that PPC's contribution to the task performance progressively reversed as the learning progressed. So like in the early learning phase, PPC inhibition during the stimulus choice epoch improved performance of the inhibited trial. Here, as you can see, there's a slight improvement in the performance. However, as performance improved, this effect gradually shifted from beneficial to detrimental, and after mice reached the expert level, when you inhibit the PPC in the same stimulus choice epoch again, their performance becomes degraded, which they have impaired performance, indicating that the PPC had become essential for the optimal decision making in the expert stage. And you can see this nice gradual decay in the delta performance, which is the performance in the optimal trials minus the performance not in the other trials. So these findings.
Okay, finish and then I will ask, but if you could pause after this slide, that would be great.
Okay. So these findings reveal a learning-dependent reversal of PPC function from mediating the history-dependent biases that we talked about earlier in learning in the naive stage to supporting an optimal decision-making in the expert stage. Yeah.
Okay, so what I understood was that if either during the stimulus or during the stimulus choice epoch, you go and you inhibit the PPC in naive mice,
yes,
then those they're less likely to show that repeat behavior after a rare rewarded trial. So
yes,
the repeat that happens after a rare rewarded trial requires PPC's intact activity during the stimulus and choice on the trial that got repeated. So basically, let's say duck is always rewarded on, most likely rewarded on left. Now, if duck comes, they go to the right, and during this stimulus choice, you go and you inhibit the PPC. Even if the mouse gets rewarded, the mouse is less likely to repeat that right choice on the next duck presentation. So you kind of messed up this stimulus choice thing, even though you didn't do the inhibition at the time of reward. So I believe that part I got right. Now we get to the expert. And now you're saying that there it did not. Well, in the expert, we don't have the repetition behavior to begin with. And now if you go, because in the expert, you said they don't repeat it after a rare reward. They just don't do it. So now if you go and in the expert, you inhibit the PPC during stimulus and choice, the performance gets worse. It's independent of that rarity effect because there is no rarity effect to begin with in the expert. It's related now to the other function of the PPC, which is about decision making. So I think there are two functions of PPC that we are seeing here. For the naive, it's about that repetition of a rare event. And for the expert, it's about impairing a choice.
Yes,
or
exactly.
A stimulus presentation.
Yes, right.
So then is that right that so then you're saying that it has an opposite effect? You mean that, but for naive, it improves it just because it impairs the repetition. Exactly. Yeah. So that's the reason. And for expert, it decreases it because now it messes up with the stimulus representation yeah.
There's a slight distinction here. So in this plot, the performance was measured on the n plus k plus 1 trial, which means the next same stimulus trial. So of course, when you reduce the repetition in the next same stimulus trial, the performance would increase. But here, what I showed is that when you inhibited the trial and measured the exact trial that was being inhibited, so this was like the previous trial.
Right.
And we also see an increase in their performance.
I see. This is on the same trial that received. So this is a different quantification. On that same trial, it increases it. what does that mean? Why would it increase the performance on that same trial?
Yeah, it's kind of like hard to answer why it increased. We are also wondering that, but we have seen that the paper from Brody's lab in the 2018 paper. So they also discovered a similar phenomenon that inhibiting the PBC would reduce a bias and immediately uh, improve performance on that trial. But their task had a working memory component which we do not have, so I'm not sure if that explanation could be applied
So
here.
if you're referring to Akrami's paper, that's the one that they say you improve performance because you reduce choice history or like basically trial history effect. So you might say then that in the naive, the reason performance improves here is that on every trial, there is a chance that they would just repeat the previous trial. And so the reason it improves is that you remove that effect. So that could be the case.
Yeah,
But then
yeah.
you're saying that this is not the case in the expert, which could be because in general, there is less trial history weight on driving the mouse's decision in the experts. So when you then this role of the PPC is not the primary one that gets disrupted. The main role of the PPC in the expert is stimulus presentation, for instance, and then that's how you impair it. Yeah, something like that. So then these were two effects. One is the performance on that same trial, the other is performance on the next trial.
Same semester. Yeah.
And then you said that in experts, it doesn't change repetition behavior.
Because in expert there were no repetition.
There was no repetition, yeah, and it doesn't. Okay, sounds good. There are a number of points. It is. It's a little bit complicated to get it, but it's very interesting. Okay, thanks.
So about the to quickly summarize the optogenetics, we found that PPC activity during the stimulus choice epoch is required for mediating the bias, and inhibiting the PPC reduce the bias without affecting choice or reward history in general in our task. And we found that PPC function shifts from mediating the bias early to supporting an optimal decision making later. So since now that we have known that PPC played these roles in mediating both the bias and the optimal decisions, we want to dig deeper to see how PPC neurons actually support or implement the bias first. And we performed textual recording in mice throughout the full learning process and isolated over 3,000 single units. And we used ANOVA and DMIX PCA to first analyze the encoding of PPC neurons and populations in the outcome epoch. And we found that in the outcome epoch, PPC encoded choices, encoded outcomes, but almost encoding no rarity. That explains why inhibition during the outcome epoch had no effect. And we next focused on the stimulus choice epoch, and we found that a large fraction of PPC neurons showed choice selectivity during the stimulus choice epoch. And on the other hand, a fraction of PPC neurons were also significantly modulated by the rare event history. So some neurons show enhanced activity following a rare rewarded trial, and some neurons show decreased activity following a rare rewarded trial. So we used an ROC-based metric to compute a so-called modulation index, and found just like almost an equal proportion of PPC neurons showing enhancement and suppression. So here we can see that the PPC neurons are being modulated bidirectionally. So how could this bidirectional modulation produce a unidirectional behavior bias? We think about combining the modulation with choice preferences and come up with a hypothesis like such a pattern. For example, if we have a right selective neuron and we have a right rare reward history, this right rare reward will enhance the right selective neuron in the next same stimulus trials. And in the next same stimulus trial, the choice is biased by this rare reward. And similarly, for a left selective neuron, a history of right rare reward will suppress its activity. And for these two neurons taken together, the choices are pushed towards right bias. And on the other hand, a leftward reward will enhance the activity of left selective neurons and suppress right selective neurons, and thereby altogether promoting a left bias. And we did find these symmetric patterns in many single neurons, as you can see these 4 examples here. And this pattern is also observed on a population level. So you can see that for stimulus A, which you have right selective neurons enhanced and left selective neurons more suppressed than enhanced. And this pattern stretches the whole population towards a biased direction. For example, you can see that the x-axis is the rare reward modulation index, and this direction is the modulation enhanced activity. Here is the modulation suppressed activity. And the y-axis is the choice selectivity index. You can see that the distribution here is stretched toward this diagonal direction, and the neurons here are enhanced right neurons, and neurons here are suppressed left neurons. And similarly, for STEAM B trials, you can see suppressed right neurons and enhanced left neurons. And these two directions match the direction of the decision bias.
Well, I'm sorry. Can you just get one of these plots and describe it? I got the model. So that part where you said that a right rare is gonna enhance representation for right choice. The model made sense, but this plot is just too overwhelming for me.
So for each neuron, we just computed a choice selectivity index and a rare modulation index, right? And for the rare reward modulation index, +1 is an enhanced activity, which means that they show a higher firing rate following a rare reward. So when the neuron shows on the right, its firing rate is higher, and when it shows on the left, the firing rate is lower. It is suppressed. And the y-axis shows if a neuron fires more for left choices or right choices. So for this plot, you can see that there are more points over here and over here. So neurons in this dimension means they are enhanced by rare reward, and they are right selective. And neurons in this dimension means that they are suppressed by rare reward and they are left selective.
Okay.
So for all the neurons that we found this stretched pattern over this axis, which means that following a STEAM A trial and the next and a STEAM A rare rewarded trial is a right bias trial. So this rare reward history would bias the whole population in two directions. It either enhances the right selective neurons or it suppresses left selective neurons.
So the choice selectivity is measured.
I don't know if that makes the explanation
I mean,
clear.
you described it very well. I could follow now. But the choice selectivity is measured on the next trial, because reward, let's say it's a rare trial and I get reward. So you compute rare modulation index on this one. And now the choice selectivity is on the next one, on the next trial?
No, the choice selectivity index is the neuron. It's over the session. So it's like we used all the trials and we did not compute for the next trial.
So each point here is what?
It's a neuron. So for example,
Each
there's
point
a
is a neuron, and it is
yeah. For example,
computed
this
trial
neuron.
averaged.
Yes, this neuron has a trial average choice selectivity index, which is located here, and it also has a rare reward modulation index, which is located here. Right?
Right. Right. So you're saying if a neuron across trials is more modulated by rare reward, then in that top case, it's more likely to have right choice selectivity. And remind us, stimulus A is associated with high reward on right or left?
So the point is it's basically the same as here. So it's like that if for a right selective neuron, like the neurons located in these two dimensions, a rare reward in a previous trial, a rare reward history would stretch these neurons to a more enhanced distribution, as you can also see here. So this distribution plot is just these neurons shown on this axis.
Yeah, except you're not saying previous trial, you're saying this is trial average, which is why I was asking if you computed the choice selectivity on the next trial, but you're saying this is just session average.
Yeah, this is just session average.
So we don't have that really, like the model assumed that this will increase choice selectivity on the next trial, if you see what I'm trying to say. So I'm saying that information is missing. Anyway, we can continue going, we're over time.
I just see your point. So you are like suggesting that maybe their choice selectivity would change in the next stimulus trial?
That was my understanding, that you wanted to say that because they get this neuron, if this neuron encodes a rare reward more strongly, it's more likely that on the next trial it will be biased to the choice associated with that. So you see basically this trial by trial adjustment of choice selectivity depending on whether the neuron was rare reward biased or not.
Yeah, right. I think we should analyze that later. Yeah, it's a good point. Okay, so should I go on?
Yeah, we do have a question for another.
You probably mentioned this.
Okay.
You probably mentioned it. Can you hear? You probably mentioned this, but how do the mice register their choices? Or
sorry, I didn't hear clearly.
The question is, how do mice report their choices?
They report choices with
it's
their
a freely
poking.
moving paradigm from what I understood. So they walk towards the port, right? Yeah.
Yeah, we use the same paradigm here. Yeah, here. They can freely move and poke into a left or right port here.
Okay, great. Thanks.
Yeah. So this pattern could explain how PBC neurons were biased or produced the bias based on the rarity being modulated by rarity history. And to quickly summarize this part, we show that PBC neurons respond to choice and rarity history, and this rare event history could bias PBC neurons by bidirectionally modulating them towards the biased decision. And we also show you that in previous behavior results that a rarity-induced bias dominated decisions early in learning, but was progressively overridden by the stimulus-based optimal strategy. And optogenetics also revealed this functional shift in the PPC. So how did PPC change across learning? We inspected PPC's encoding of choice, stimulus, and rare reward history during the stimulus choice epoch across all performance levels. And we just demonstrated in the last part that rare reward history is the reason that implements the choice bias. And here we found that an increase in the stimulus representation in the PPC at both single neuron level and population level. And shown here by this is the ANOVA analysis, the DPCA and D prime here. This could explain how PPC increasingly supports stimulus-based optimal decisions. However, while yes?
Maybe you were going to say, sorry if I... So why is there a decrease in choice? That is very surprising. That's opposite of what I found in my postdoc.
Yeah, the choice is actually decreasing.
But why?
We think
I found completely the opposite of that. That choice was increasing.
We think the reason that the choice was decreasing is kind of like because there are less predetermined actions. Like for example, when the performance are higher, there were less perseverance behaviors or any other kind of bias behaviors. That's our guess for that.
With your type of task that is because it's very much of perseverance, as you said, because the one side has higher reward probability. So, but the task that I had was just decision making, no bias. Like it's just evidence, you make a decision, accumulated, make a decision, and with that, definitely choice representation was going up in PPC. Here, you're showing in a task where the majority of choices, where there is this distinct reward probability between left and right. So in a task that choices are more driven by bias, you see less and less representation of choice by PPC, which is a little bit opposite to what we think PPC does, which is related to trial history. But I guess you're saying that... Yeah. Go ahead.
Yeah, I think there could be another reason that the choice encoding is decreasing here, because these mice were never trained on any other task, and I don't know if your task is based on a previous smaller task, because in our task the mice were never trained on any task, and they simply entered our task. So the performance here,
mine
like 50%.
Was similar. So my mice were naive, and then they were only trained on one task, which was the task, and then over. I had the exact opposite. That the performance for me, if you look at my paper's figures, is correlated with the choice representation. The stronger the choice decoding, the better the performance. Like completely opposite to what you're showing. But you're showing that
also another possibility, because our task is auditory based, right? And there are so many papers saying that PPC does not play a causal role in many auditory based decisions, right? There are so many papers saying that. And maybe for an auditory task, PPC is indeed not required. So we can see this drop. I don't know what kind of task that you're running on.
That was visual and auditory together, but if I want to say which one was more dominant, I would say the visual. The auditory is more likely, but it was audio-visual together. Question, the x-axis here, that performance is pulled across naive and expert animals. So should we more think of this as naive on the lower side and expert on the right? Or is this computed on a... Right.
Actually, so each point is like a running average of 5% around this point. So
right. But you're saying that the
the
better the performance, the more expert the animal, the better the representation of the stimulus, but the worse the representation of the choice, which is
yes.
very complex. It has to do with how your task is designed, which is one stimulus very much rewarded on one side, another stimulus, or there is this ambiguity. So in my task, one stimulus 100% rewarded on one side, right? In your case, there is this ambiguity, that there is this uncertainty component. So it seems like when there is uncertainty in the task, in the outcome of the task, then choice representation goes down. But when there is a definite relation between stimulus and choice, so it seems like the PPC learns that there is uncertainty in this task, and then it says, I'm not going to represent the choice. So the PPC is more likely to represent the choice when the stimulus choice contingency is 100% certain. But then how do we put this together with the trial history effect? Because early in training, why is it that early in training the choice is so strongly represented? Perhaps because at that time there's a big trial history component. Later, the mouse learns not to use trial.
I suddenly remembered a result that we did not put in the manuscript. As you can see here, the choice is indeed decreasing. So here is the percentage of encoding neurons. They are decreasing, and the population encoding is decreasing. But the discriminability, the deep prime analysis, shows that the choice encoding is relatively stable across all the naive, intermediate, and expert stages. So the deep prime values were almost the same across all three stages. We did not show here, but I remember we do have that result.
So the deep prime you mean computed for single neuron? So you're saying there's a difference between single neurons and
the... We were computing deep prime using 200 neurons shuffled. Yeah, I think.
If I want to make a guess randomly here, I think what you're showing in that top left panel, that the choice percentage of significant neurons for choice decreases. If I want to make a guess, is that there is confounding effect here from trial history. And if you do this analysis accounting for trial history, I think this will give us some insight. But I think the reason you see this decrease of choice significance neurons with performance is confounded with the trial history. That's my guess. Okay.
Yeah. So yeah. So here I just showed you that the stimulus encoding in both single neuron level and in the population level is increasing when performance is going up. However, what we found that the rare reward history encoding in the stimulus choice epoch remained relatively stable across all performance levels. Although that in behavior, the stimulus-based strategy already overrides the rarity-induced bias. And we also found that each neuron's stimulus selectivity was not correlated with the rare reward modulation index, which means that the stimulus processing and the rare reward modulation within the PPC are likely to be parallel to each other. that they are not like overlapping, they are not dependent on each other. So this behavior shift from the bias to the optimal strategy does not necessarily mean that the PBC have to forget this bias representation. And when we looked deeper into the way that PBC encodes stimulus, we found that the stimulus encoding in the PBC is even independent of the choice selective neurons. So you can see here that the stimulus did not bias the choice selective neurons towards the correct choice in the expert stage. It's unlike how rare reward history modulated these choice selective neurons. So back in there, a rare reward history would stretch the population towards the biased choices. But here, you do not see, for example, a stimulus A that driving all left selective neurons, or stimulus B are more driving the right selective neurons. And this means that the optimal strategy that the mice shows would operate through a stimulus-based pathway, and this pathway is in parallel to the rarity-induced bias circuits, while both circuits coexist in the PBC. Yeah, and to quickly summarize this part, we show that learning would recruit PBC neurons to encode stimuli, while the rarity history representation remains relatively stable, and the stimulus-based optimal strategy operates in parallel to the bias in the PBC. So this comes the last question of my talk, though. Considering that the rarity bias impedes learning, and the stimulus-based strategy would support learning. So these two functions coexist in the PBC, but they drive learning in opposite directions. So what is the learning process in this task? We want to know that how the two roles drive learning. So this time we decided to use a model-based approach. We adopted a so-called two systems approach. So it is a fundamental idea in psychology, and it basically says that humans and animals they have two ways of thinking. One is fast thinking and another is slow thinking. And the way that the bias and the optimal strategy works just resembles the two systems. For example, the rarity-induced bias occurs in the naive stage, and it is suboptimal, which looks like a system 1, and the stimulus-guided choices is an optimal decision, and it is slow and it requires effort to learn it, so it looks like more like a system 2. Therefore, we built a simulation model based on this two systems framework. So it's basically a dual agent model with two systems. We have an first agent implementing the rarity-induced bias, and a second agent implementing a stimulus-guided choices, which is the optimal strategy. And the first agent is based on a win-state-lose switch framework, which we incorporated a rarity factor into it. And the stimulus-guided system is just a reinforcement learning mechanism. So to quickly go through it, we have to detect the rarity state in the model. We used a fast learning rate and a fast value. So basically, how do we detect the rarity in the model? We simply use a prediction error, which is an absolute prediction error. So for example, you have like let's show you the result. So for example, when an outcome, you have this model will successfully show the simulation results that successfully resemble the occurrence of rare trials. And to simply say it, we used an unsigned RPE, which means that for a let's take 80-20 as an example, and the fast value would update would have a high learning rate, and the outcome when it's a rewarded trial, when a rare reward occurs on the outcome, the prediction error is quite big, and when the absolute prediction error is bigger than a defined threshold, the model will report it is a rare event, and otherwise it will report it is a common event. So this is basically the philosophy behind the rarity state design. And besides that, we also have an extra pair of probability of repeating. So these two parameters means that if it is a rare event, how much extra probability will you add to the current win state lose switch probabilities? Yeah, we also have this these two parameters here that show that calculates the repeat probabilities for the common trials. So here for example, if a previous trial is a rare trial, is a common trial, then the gating mechanism is like it gives a 0, and the extra win state lose switch probability is not added to the common trials win state lose switch probabilities. So the choice is simply based on the common repeat probabilities. And when a previous trial is a rare trial, and the gating mechanism opens, and the common repeat probabilities will be added with an additional factor that defined here. And yeah, this is how the rarity-based win state lose switch agent works. And for the RL system, it's much simpler. It's basically a Q-learning agent with some modifications. We incorporated a multiplicative rule in the RL agent so that the model could reflect the decay period that animals would usually show during the early phase of learning. And we also used different learning rates for rewarded and unrewarded trials based on this paper. And the choice output of the RL agent is generated with an additional Gaussian noise and a softmax rule. And to integrate these two agents, we adopted an entropy-based method. So previously, we found that the encoding of stimulus is increasing gradually, and the encoding of rare reward history remains stable, right? So based on this observation, we used different decision weights for the agent 1 and agent 2. The intuition here is that since the rare reward history encoding remains stable, so we set the encoding weights. So we set the decision weights for the win state lose switch agent to be a constant 1, and the decision weights for the Q-learning agent to be a dynamic, which is based on the Q values learned through the system. So when the performance is increasing, the Q values for left and right, the distribution of these Q values would gradually separate to different two distributions. And when the distributions are more separated, the entropy of the Q value distribution will increase. And therefore, when the entropy increases, the decision weights for the RL agent will also increase. And therefore, the RL agent will gradually override the output of the win state lose switch agent, and finally becomes the dominant in the choice output as the performance gets higher. So our model successfully replicated the graded strength of the rarity-induced bias under different common to rare ratios, and the model also predicted faster learning at a lower rare event rate consistent with the mouse data that we observed. So it's basically like you have less rare events and you will learn faster. And to simulate the optogenetic effects, we performed in silico inactivation by inhibiting the specific model components. And we found that disabling the rarity state here in this rarity-based win state lose switch agent could eliminate the rarity-induced bias in the naive stage. So you can see here. And disabling the RL agent, the agent alone in the expert stage could mimic the impaired performance in the inhibited trials in the PBC, and we combined these two approaches together to simulate a full PBC inhibition in rare trials. So here the model is inhibiting both the rarity state and the RL agent together, and this inhibition predicted that the stimulus and choice of inhibited animals should learn faster. And we go back to re-examine our optogenetic data, and we found that that is the true, that the stimulus and choice inhibited animals did learn faster and required less trials to reach the expert stage. So this supports that PBC may also have a causal role in the learning of the task. Yeah, to quickly summarize the whole talk today, we found that a statistical rarity would drive the decision bias in both humans and mice, and we found that this bias had a persisting, influence-resistant impact on choices. And in mice, we found that PBC mediates both the bias and the stimulus-guided optimal strategy. And the PBC mediates the bias by bidirectionally modulation from the rarity history, and learning would recruit PBC neurons to promote the stimulus encoding to gradually support optimal decisions. And the bias and the stimulus-based choices operate in parallel in the PBC. And lastly, I'd like to thank Dr. Yang for her support for this project, and my collaborators and assistants from Huang Lab, and all helpful comments. And thank you, everyone, and I look forward to your comments and questions.
Awesome. Thanks a lot. Very, very good. Half an hour above time. I think the whole modeling work could be its own talk, and I'm very interested in that. We also have some modeling work going on in our lab for a relevant task. So maybe we just organize something separately to go more carefully through the model. But it was amazing. I think the questions, the design, the findings are really nice. The difficult part is that there are a lot of conditions, and in some of your analysis, I would say you could try to separate conditions more carefully, so the effects are not confounded. And I think that can lead to a lot cleaner figures that are more easily accessible for the reviewers and for the readers. But other than that, I really like the work. It was a ton of work, and the model, I'm super excited. So maybe we just we'll be doing another session on that at some point. Yeah, thanks a lot. I guess we are already over time, and yeah, that's it. Have a good day.
Okay.
Thank you.
Yeah, thank you so much.
Bye.
Bye.